Okay, and we're recording. Okay, so here's what we were talking about last time. Oh, forgot to pull this down. Oh, and I hope everybody had a good break. Nice to have a couple of days off in the middle of the semester. Hope everybody was able to get in some relaxation and stuff. So jumping back in, here's what the very last thing we talked about, and that was that, when you have, well, and of course you usually do, have two different orders in which you can slice, right? Doing a double integral. Very often they're not equally desirable, right? And, this is not a horrible example, but all else being equal, I think most people would prefer not to have square roots in their bounds, and there's a temptation to say, who cares, it's just in the bounds. You're just going to plug that in after you do the antiderivative. The problem, though, is that, sure, it's plugging in at the end of doing this inside integral, but that whole inside integral, square roots and all, is the integrand for the outside integral, right? So square ugly in your inner bounds means you have ugly in your outer integrand. So highly desirable to avoid, and again, depends on what that f function is as to just how bad would this turn out to be. So again, how do you avoid this? Well, rough rule of thumb, whatever you view as being your most clearly desirable as an input variable, and here I think x, pretty clearly what we want to view as the input variable there, right? Put that on the outside. You put that on the outside, and then you won't have to solve for it. Roughly speaking, is the upshot there. Okay, so that's a good lesson, and I hope y'all will let this guide you in when you're deciding which way to do your slicing. Now here's another example that ends in a nice moral, a nice strategy. So here we have a triangle with certain corners, and here it is. It's not hard to plot out that triangle. All the edges are lines, and with lines, not a particularly strong motivation to view either one or the other of the variables as being a function of the other. I mean, they're kind of equally. I mean, if y is equal to x, which one's the input, which one's the output? Kind of who cares, right? So what's our motivation here? We're going to try it both different ways and see what happens. Starting with doing your y integration on the outside, y goes from 0 to 1, and then we fix a value of y, and for that value of y, we're going to now look at our x bounds. Let's see here, x lower bound is defined by that point, which is on that line, which gives me that lower bound. Right, and then the upper bound for x is defined by that point, which is on that line. Bam. Okay, so that worked out really nicely. All right, is everybody with me? Everybody see how that worked? I went through that really quickly, again, because we've gone through a bunch of examples at this point, and I skipped a little bit of algebra there that y'all can do on your own. Okay, so that worked out just fine. Now let's do it the other way. Let's see what happens. Same domain here, you'll notice. I'm going to first do x slicing this time, and it's tempting to say, well, I can just have x go from 0 to 2, and now let's think about what are my y bounds? Well, and I'm going to go straight to the punchline. The upper bound is defined by points like that, but the problem is it's on that curve for a little while, and then it's on this curve after that. Right? Keeping in mind, so for a given value of x, given a value of x, my upper bound for y is defined by two different curves. The lower bound for y, no problem. The lower bound for y is just 0. No issue. So, okay, how do we deal with that? Can I solve for y as a function of x on a pair of lines? No, tragically I can't. So what I have to do here, and this is really undesirable, but I have to first say, look, we're going to look just at these values of x first. Just for those values of x, I can talk about the upper bound for y as, the upper bound for y is defined by that point, which is on that curve, which has easy given equation, and thus that upper bound for y And then I entirely separately have to say, yeah, but we also have to look where x goes from 1 to 2. Everything's different as x goes from 1 to 2. As x goes from 1 to 2, my upper y bound is now defined by that point, which is on that curve, which has a different equation. And thus I get a different upper bound for y. So, punchline, you have to have two integrals. You have to break up the domain effectively into two separate chunks, right? We're going to cut the domain in half effectively right there. And we look at this half first, and then we look at that half next. And again, I think that's pretty undesirable. You look at your two choices here. Which of these slicing orders would you prefer? Which of these resulting iterated integral situations would you rather compute this or would you rather compute that? No particular one of these integrals looks like it has nastier algebra, but this has twice as much of it. Okay. How do we avoid this problem? I don't want to end up with two integrals when if there were a clever way to just automatically get to the one every time, then that'd be really nice. So here's the idea. The problem was that we have these two different upper bounds for y in this case. Why do we have two different upper bounds? Well, because I was solving two different equations. Why was I solving two different equations? Well, because I was looking at two different lines. And when you have two different lines, when the point that you need to focus on, right, was on one line, then goes to another line, it had to at some point turn. It had to at some point jump from the one line to the upper line, which you would expect to happen at an intersection, which typically makes a corner. And so this is my rule of thumb. It's just this is not a law. This is not a always kind of a situation. But good job, rule of thumb. Try not to slice through corners. Yeah, here we go. So try not to. Oh, whoops. Here we go. Try not to slice through corners. And notice as we did our x slicing here, that's exactly what we did. As we were going perpendicular to the x-axis, as we were going through along like this, boom, right there, I sliced through a corner. And then naively hoped that I could just proceed as if nothing ever happened. Right? But that's the tip-off. If, as you're doing your slicing, if you slice through a corner, probably that means that you're going to have, I wanted the red, probably that means that you're going to have to end the integral that you were looking at and start a whole new integral. What do you think? Everybody kind of see the idea there? Now, a clarification real quick. You're going to usually, very often anyway, kind of slice through corners at the start and the beginning. So here, as I did my y slicing, there's my first y slice. I sliced through two corners with one slice. Gonna have to start a new integral there. Fine, I was starting a new integral there anyway. Not a problem, right? And then everything's fine. And then here at the end, I sliced through a corner again, but I was done anyway. So it doesn't really matter. So when I say try not to slice through a corner, what I mean is try not to slice through a corner mid-process. Okay. All right, what do you think? Everybody happy with that? Yeah.
Can you just go over again why it's y and 2 minus y?
Yeah, so that's right. So if you look at the upper, where does this upper bound here come from? It comes from the fact that this point is on that curve, which has an equation you can write down, and if you then solve for y, keep in mind we're looking at y, right? This is the formula for y. Y is x, right? So on the upper bound, upper bound for the next region for these other values of y, it's this point which is on that curve, right? Which has a different equation. I'm sorry?
The equation on top.
Oh, okay. You're wondering where this came from. Yeah, okay. So that's the upper bound for x. That's looking for this, right? Keep in mind we've got y going from 0 to 1, right? We're fixing a value of y. For that fixed value of y, somewhere between 0 and 1, My upper bound is defined by that point, which is on that curve. You write down the equation, x plus y equals 2, right? Solve for x, and you get that. Yeah. Yeah. Okay. Well, let's see here. So sometimes, now this is just in the way of another category of examples that you'll see sometimes. Sometimes the domain isn't defined as part of the statement of the question. Sometimes you have to think about the geometry of the situation and, how are you choosing to analyze the problem to be able to decide what the domain actually is. And so here's a easy example. Suppose we've got this surface here. That's our typical paraboloid. We've got this surface here. That's some plane, right? And let's look at the volume between those two. Well, the volume in between those two surfaces is going to be something that looks kind of like this. Well, here it is. There's a better, less obscured picture of it. There's our volume in between. Let's compute that volume. Well, the first thing we can do is take a Riemann sum approach to this and say, well, I'm going to take this volume, I'm going to slice it in two different directions. I'm effectively going to slice up the shadow. I wanted purple here. I'm going to slice up this shadow down here. And then we'll, one at a time, looking at those pieces, we will, like little bitty pieces like this, we'll ask how much volume is there above that little slice of area. And we're looking then at the volume of these little, as I like to call them, French fries. Right, we'll add up the volumes of those French fries. French fry volumes are height times the area of the base. Right, this is all straight up Riemann sum, chop it up, add it up approach. Except again for the fact that we don't yet know what our domain is. Right, so what's our domain? And this is a tricky part. Let me first show you what a lot of people do wrong. This is very tempting, it seems, for a lot of students. A lot of students say, okay, well, I'm interested in this curve that sort of bounds my domain. That curve, of course, comes from this edge, if you will. That edge comes from where these two surfaces intersect, and my surfaces are, well, that and that, right? There's the green surface, and then here's the blue surface. I want to know where the green intersects the blue. So the mistake, this is all right so far. The mistake that students make then is they think, okay, well, then I want both equations to be true, and therefore I'm going to set the equations equal to each other. So I'm going to do this in red to emphasize that this is not true. A lot of students say, well, I'll set these equations equal to each other, and therefore x squared plus y squared must equal to this. And that's wrong. Now, just to emphasize why that's non sequitur, here's a silly counterexample. Let's suppose I wanted this equation and this equation to both be true at the same time. Would I set those two equations equal to each other? No, that's silly. This is just not an algebraic thing. Setting equations equal to each other is not an algebraic thing. Right? It just doesn't make any sense. So don't step on that landmine. Don't make that mistake. Now again, it was all good in terms of defining that purple curve. That purple curve here, this intersection of these surfaces, is indeed what we need to get our hands on. We have to be more careful how we get our hands on it. And the way we get our hands on it is to recognize that for some points, right, like this point here kind of in the middle, when you look at how far you got to go up to get up to the plane, right, and you look at how far you got to go up to get to the paraboloid, you have different distances that you have to go up. Namely, there's different z's corresponding to this x and y pair down here. Right. And I point out that the intersection point that we're looking for, points like this, that are actually on the boundary of our domain, Those being the points that we're looking for. Those are the points where the surfaces intersect. Therefore, those are the points where the distance you go up to the plane, same as the distance you go up to the paraboloid. But keep in mind the distances that you go up are z's, right? So it's not that I want the equations to equal to each other. It's that I want the z's corresponding to given x's and y's. I want those z's to be equal to each other. So we're not going to set this equal to that. That doesn't make any sense at all. What we're going to do is we're going to set this z equal to that z. Does that make sense to everybody? Does everybody see how the geometry actually supports that? Right? Okay. So you got to have to solve for z in both of the equations, and conveniently one of them's easy. But setting the z's equal, you get this equation here, and that it's all downhill. It's all just sort of algebra 2 from here on out. Well, in particular. And by the way, make sure that you're good at this. A lot of students maybe kind of are a little rusty on their algebra 2 or whatever they call second year algebra in high schools these days. In order to make sense out of what this equation is, you have to do this move called completing the square. So make sure you're good with completing the square. A lot of people think that completing the square is kind of obviated by the quadratic equation. This is not true. Sometimes I'm not solving for anything. I literally need to redo the algebra. And so completing the square allows you to turn this, I don't know what that equation is, into very clearly the equation of a circle. Okay. All right. Okay. Moving along. This book makes some, I think, kind of odd decisions about how they break up the content of the material into sections, right? And so they have some sections that are just massive, huge collections of tremendous amounts of things that could have been broken up into smaller pieces. Give me 2 seconds. Then they have this little oddball section, section 5.3, that has basically one idea in it. So I have 1 page of notes for section 5.3. But again, we've already seen some, and we're going to see more again where the sections are just massive. So anyway, it's going to take us about 5 minutes to go through section 5.3. Go ahead, I'm sorry.
I just had a quick question about the last thing.
Yeah.
So when we're finding that equation of the circle, does that give us a balance?
Yeah. Right, so what that is, this equation here is the equation of that circle. And it's the circle that, again, the motivation for it was to think about this ellipse up here, but the reason specifically what we care about this ellipse is what's its projection of the xy plane look like, namely what's the relationship between x and y, and here's the relationship between x and y. Is that good?
Yes. Okay.
Yep. So when it comes to actually slicing, in some sense I didn't finish this example, but I got to the part that I wanted to really get to. But if you really wanted to finish computing this volume, you'd have to take this equation, defining our domain, slice and dice in the usual ways, decide if you want to solve for x as a function of y or y as a function of x, and it's going to be a little annoying whichever way you do it, right? Iterated integral follows. Yeah. Cool. All right. Yeah, so arguably this could have been an example in section 5.2. Sometimes when you are asked to compute an integral, notice this is an iterated integral. Sometimes that's just, they've given you the wrong way to compute a double integral. This order of integration is just bad for this particular integral. And in case y'all might not recall, this inside integral here, integral e to the x squared, there's no closed form antiderivative for that. In other words, there's no amount of trickery that you can play with integration by parts and substitutions and stuff like that. You just can't do it without writing it down in terms of infinite series. So this is very unfortunate. And it turns out that if you change the order of integration, if you just say, look, this iterated integral represents a double integral, I'm just going to slice up that double integral in the other order, right? Then the problem sometimes just kind of goes away. Not always, but sometimes. It's something that's worth trying anyway. So here's the idea. Step one, we're going to figure out how to turn this iterated integral back into a double integral. And then we'll just slice it up after that. Okay, so notice this integral. Y goes from 0 to 1. Okay, so these are my first and last Y slices in the slicing process. So my domain is in between these two lines there. Then let's see here. For any given value of Y, x equals Y is my lower bound for x. That's that line. Right? And then let's see here. X equals 1 is my upper bound for x. So we're slicing from that Y value to this Y value. And then for each of those Y values, x goes from light blue to dark blue. So we have now reverse engineered that this is our domain. Right? So this iterated integral that we were given as an iterated integral, I can now reinterpret it as a double integral. Whoa, too far. Sorry. Double integral. It's just a double integral over that domain. What do you think? Everybody good? So with a double integral over that domain, just slice it up in the other order now. Now I'm going to do my x slicing on the outside. X goes from 0 to 1. And then for any given value of x, let's see, I've got y. Y starts at this line, which is y equals 0. Right? And then we end at this line, which is where y equals x. So there's just sort of the opposite slicing. And as it happens sometimes, problems just go away. And that's what happened here, because this inside integral, no longer a problem. Sure, there's that scary e to the x squared again, but x is not a variable, right? X is a constant, y is the variable. So this is actually the world's easiest integral. This is integral of a constant. An integral of a constant's nothing to it. So now we get to the, you could say, okay, but now this though is where it's really scary. Here's where I've got that e to the x squared, and I'm doing the x integral. But because I did the y integral already on the inside, I've got an extra factor of x here. And this is just an easy substitution. Just let u equals x squared, du, etc., and all falls into place. And it's not a problem. So, anyway, tool for your toolbox. If you find yourself with an iterated integral given to you, right, and if you're having trouble computing it, reverse engineer the domain, slice it the other way. Okay, that was section 5.3. Okay, moving on then to 5.4, triple integrals. A lot about triple integrals is really kind of the same stuff that we've already done. It's like double integrals, just a little bit more so. Double integrals, recall, were about taking a domain, chopping it up into little pieces, and then adding up easy answers on those little pieces. So chop it up, add it up on a two-dimensional domain. Triple integrals are really just chop it up, add it up over a three-dimensional region instead of a two-dimensional region. And everything sort of changes accordingly, but it's strategically same idea. So, for example, maybe I've got a three-dimensional region like this, and again, we're going to start with rectangles because they're a little bit easier first go. Got a rectangular box, and it's full of, dirt, something, trailings from a mine, perhaps, right? I don't know. And the thing is, the way the trailings fall into the box, maybe there's more, ore and such in this corner over here, and then there's kind of more dirt in the middle, and then maybe there's kind of air gaps. It's not packed as tightly over in this, near the top. whatever. Maybe there's more dampness, more water kind of in the bottom. The density is a function of position all throughout this box, right? How much total mass inside of the box? Well, fundamentally, the mass is distributed over a solid, right? I can't just say, oh, well, we'll look at the shadow down here. It's tempting to try to make a double integral problem out of this. We'll look at this shadow. Look at little pieces there and ask, well, how much mass is there, sitting over that piece down there, this little piece of area? How much mass is sitting over that piece of area? Well, I don't know, because the density is very different at the top and very different at the bottom. So breaking this up as a double integral does not simplify the problem. But if I break it up, not by chopping up the area of the shadow, but if I actually chop up the box itself, slice it in all three different directions, and I get not a bunch of French fries, I get a bunch of little what do you call this in cooking? Is that a dice or a julienne? I forget. Anyway, a bunch of little tiny little boxes like this, little sub boxes, right? Density is approximately constant on these little boxes, and it's different up there and it's different over. It's different all over, but on any given box, the density's pretty constant. And so on this little box, density times volume, nothing to it. Mass per unit volume times volume. All right. And then just add up over all the boxes. So here's the definition then of a triple integral. It's chop it up, add it up. Where we're looking at volumes of little boxes. Volumes are height times width times length. So delta x, delta y, delta z. On each of those pieces, we're going to compute the answer to whatever our question is. Mass per unit volume times volume. Or maybe you're computing something else. You've got some other, quantity per unit volume times volume. Whatever it is the problem is, the integrand is appropriate to the application. But in purple here we have the answer to whatever the question is on our little box, and then we add up over all of the little boxes. Does everybody see how strategically it's just like double integrals? It's just, a little bit more so. Right? We have to add up in three directions instead of two, because there's, you got to go all the way this way, you got to go all the way this way, and you also got to go all the way that way. So three indices, I, J, and K. Thus, then, three stretched out S's to make the triple integral symbol, right? So triple integral. Just, same motivation as with a double integral. And again, we integral shorthand represent this little piece of volume, delta x, delta y, delta z, with the V for volume. Okay. All right. How we doing? Everybody okay with that? There are some little details you do have to kind of pound through to be precise about this. We've already talked about how you slice up the interval from A to B on the x-axis. We have formulas for that. We then talked about how to slice up C to D on the y-axis. We did that for double integrals. Okay. So now we have to also slice up, from E to F on the z-axis. So sure, a little bit different formulas here, but they're morally equivalent, right? Same basic structure. It's just now E to F instead of A to B. Morally the same. Okay. All right. And again, ignore all that the book has to say about irregular partitions and test points. That's formality that's admirable, necessary in 400 level math classes, and totally unnecessary in Math 219. Yeah.
So you would know to use a triple integral if your function was changing with respect to z? Like, how would you know to use a triple integral versus double integral?
you have to ask yourself, how is it that you're breaking up the question, right? So if you're breaking up your question into little rectangles, then a double integral is fine. And so if you look at, for example, this question here, right? So we're breaking up the volume, we're breaking up by understanding little pieces of area, little rectangles of area down here in the shadow, right? I'm not, and you can even see that I'm not, breaking up the volume itself into little pieces of, rectangular box of volumes, right? So the domain, the thing that's being broken up into pieces, what you could reasonably call small pieces, is the shadow, not the solid here. So that's kind of the giveaway. Whereas here, I'm literally having to break up the volume itself. And if you try to only break up the shadow, then you get, again, these tall, skinny, the density is just not constant over there. Yeah. Is that satisfying?
Yes.
Okay. All right. Yeah, so this is the motivating examples. We've already kind of done it, but let me again show you how to write this down. Suppose then that I want to compute the mass in a rectangular box with a given density formula. Well, chop it up, add it up. Total mass is the sum of a bunch of little pieces of mass. I recognize that I'm breaking it up into pieces in three directions, what you might call three-dimensionally small pieces. By the triple integral symbol. On each piece, mass is mass per unit volume times volume. Again, appropriate to how I'm breaking up the solid, right? I got little pieces of volume where the mass is. And I've got myself a triple integral. Okay. All right, now you'll notice I did something a little bit unusual here. Most kinds of integrals that we've seen to now, I've motivated with what you might call graphs, with standard geometric examples. For everybody's first single variable integral is to compute the area under a graph. When we did double integrals, the very first example that I wrote down was, suppose I want to compute the volume under a graph of, now it's a function of two variables, right? But it was area under a graph, then volume under a graph. Why didn't I do something like that here? Why do I start off with my motivating example not being geometric, not being about graphs, but being about mass? Right? Why didn't I give you the geometrically satisfying picture? And, well, here's the reason. Again, with single variable integrals, you can talk about the mass of a rod, or you can talk about the geometric, area under a graph. And this, arguably, the picture on the left, more satisfying. I can see the integrand in the picture. We like that. You look at the two-dimensional examples, double integrals, very satisfying to think of them as computing volumes. Again, I can see the integrand. This F here, its height. I look at it. The picture's a little harder to draw, but still, it's visually satisfying. And of course, you could also use it to compute mass distributed over a two-dimensional region. And here's the problem. For triple integrals, notice the pattern. For a single variable integral, I had a two-dimensional picture. For a double integral, I had a three-dimensional picture. If I wanted to continue this pattern, if I wanted to make a sense out of a, sort of a standard geometric, let's look at it from a graph point of view. For triple integrals, I would have a four-dimensional picture, and that's not on the table. We just can't do it. I can't even fake it. So, not a good way to think about triple integrals. By comparison, let's look at the mass metaphor, the mass application. For a single variable integral, we get a one-dimensional picture. For a double integral, I get a two-dimensional picture. And then for a triple integral, I get a three-dimensional picture. And yeah, a little harder to draw than two-dimensional, but totally doable. Everybody with me? So here's the problem, and this happens a lot, and it's a problem for a lot of students. A lot of students pick their favorites their favorite point of view, sort of one dimension at a time, and say, okay, I'm going to think about single variable integrals this way, I'm going to think about double integrals this way, and, okay, I guess I better think about triple integrals this way. And then there's this ever-present question then of, okay, well, let's see here. I got a three-dimensional picture there. I got a three-dimensional picture here. What's the difference? How come this is a double? How come this is a triple? They're both three-dimensional pictures. Possible source of confusion there. Right? So what I advise, this is yet another argument, I think, against the graph point of view on things. Now, it has its place. I'm all for it in certain contexts. Yes, absolutely. But not only do graph, area volume kind of concepts not directly connect to applications, right? I've complained about that quite a bit. Applications that you're interested in connect to Riemann sums. They don't connect to area. They don't connect to volume, right? But furthermore, it sets up an unsustainable pattern. Right? So I encourage that you think about integrals from not only from a Riemann sum point of view, but if you want a physical, intuitive kind of way of thinking about it, I encourage you toward the mass point of view. Mass is distributed across an interval. Fine. If it's distributed across an area, cool. If it's distributed across a solid, no problem. Same story. So, like I say, I encourage this point of view. Again, don't abandon the graph point of view entirely. Yeah, it has its moments. Just don't hang your hat on this. Don't let this be your cornerstone point of view on integrals. Okay. Everybody comfortable with the point there? Okay, yes?
I'm a little confused about the mass of the, single integral.
Uh-huh.
Are you considering it as an infinitely thin rod?
Yeah, not necessarily. I mean, so here's a hopefully relatable example. I as a homeowner spend more time than I should at Home Depot, right? And here's the thing: when you buy chain or rope or whatever it is that you're buying that is measured by length, right? They're not infinitely thin, and yet if you talk about how much does chain weigh, they'll talk about it as how much it weighs per foot or, per meter or, wouldn't that be nice? Whatever, right? It's so the unit of length. So it doesn't have to be one dimensional. It just has to be understood in a linear sense. And so, if you had a really long, pipe, or something, right? And you wanted to talk about, how much water is in this pipe. Then you talk about the mass of water per foot in that pipe. And of course it's understood that, the pipe's a pipe, and but the cross sections are all the same. We don't really need to talk about that. And so you just understand it per length. Does that make sense?
Yes.
Yeah. Okay. All right. Okay. So, at this point in the discussion of double integrals, I made a connection between double integrals. We're now talking about triple integrals and iterated integrals. And the claim was, you could compute the standard geometric example, volume under a graph surface, right? You can compute that either way. You can compute it with a double integral. You can compute it with an iterated integral. So computing the same thing, you get two different answers. Those two different answers have to be the same. I can't give you that argument for triple integrals. As previously noted, right, if I were to give you that argument for triple integrals, that picture would have to look like this, which we can't. Right? So I can't give you that argument. What I can do, though, is assert, and I hope you're willing to take my word for it here, that the pattern continues. There is a really good, much better, in fact, rigorous algebraic point of view on why triple integrals can be computed with iterated integrals. Again, it's beyond Math 219. It's not our focus, just not what we're here to talk about. So I'm just going to assert that, I'm going to say just like you would expect, triple integrals can be computed with iterated integrals morally for the same reasons. Okay. All right. So again, here we are with our diagram, our sort of strategic diagram of triple integrals. We've seen that mass can be written as a Riemann sum, aka triple integral. I claim many other applications as well can be rewritten as Riemann sums, aka triple integrals. Not only can't they be written as whatever that geometric object would be, we don't even know what that geometric object is, right? So don't even think about doing that. It doesn't make any sense. Again, don't try to immediately write them as iterated integrals. It doesn't make any sense. You can't talk about mass per unit volume times the length. That doesn't make sense. That's a mismatch. Right? The Legos don't fit together. So those roots don't work. But again, thankfully, triple integrals can be turned into iterated integrals, and iterated integrals can be cranked out with a fundamental theorem. So we've got the same sort of strategic process, 3 steps. Step 1, turn your application into a triple integral. Got to write that down. Otherwise, you're doing this. Right? So, application as a triple integral. Rewrite the triple integral as an iterated integral. Compute the iterated integral to get your answer with the fundamental theorem. Okay, so, for example, how do I compute the amount of mass in a rectangular box with the mass per unit volume given? Step 1, mass is triple integral. Already argued, right? The total mass is the sum of little pieces of mass. Mass per unit volume times volume, right? This is straight out of the previous examples. Step 2, triple integral is an iterated integral, and let's be careful with the bounds here. We've got x going from 1 to 2. Notice my x bounds, 1 to 2. We have y, y, come on, stylus, y going from 0 to 2. Notice my y bounds. Man. Y bounds 0 to 2. We've got z going from 0 to 1. Notice my z bounds 0 to 1. Notice also, I was not particularly thoughtful about the order that I put these differentials down. You can put these differentials down in whatever order you want, because we have a rectangular box. And again, this is the special domain for rectangular boxes and only for rectangular boxes. You can do the differentials whatever order you want. You just change around the bounds accordingly, right? And that's all good. And then step 3, punch it out with a fundamental theorem. And so, bunch of computations ensue. Be careful to pay attention to which variables are playing what role at what point. All the same rules apply for this inside integral. Notice that x and y are both further to the outside. X and y then are both to be treated as constants, and they just kind of come along for the ride. It is z here that is your variable. So we're integrating just the z, and of course the 2 is also a constant. Anyway, the antiderivative of 2z is z squared. The x and y remain as they are constants. Yeah? Okay. Alrighty. I'm going to let y'all read through these details. Again, it's just like with double integrals. It's just, 3 steps instead of 2 steps, but all the same ideas. Okay. Alright. Here's where it gets fun. Challenging. When you have a non-rectangular domain, what do you do? And again, how did I deal with this with double integrals? I drew a 3-dimensional picture. I talked about the volume example because it's visually relatable, and that's nice, and I wanted y'all to have that satisfaction for double integrals. Again, if I were to do the analogous thing here, it'd be a 4-dimensional picture. I can't. Just can't do it. So again, I'm going to ask you to trust me that everything works out analogously. I claim it does. I think it's highly believable. And here's that process. you pick a differential, whatever's going to be your outside bound, slice or perpendicularly to that coordinate axis, just like we did with double integrals. So, for example, here I am doing x on the outside, and so x goes from there to there. Here's what my slices look like. All right, so we've got our x slicing. You got to identify the bounds by the starting and ending points. Come back down here to the picture. The lowest value of x corresponds to that very first slice. You might say that slice way back in the back, the very first, one of these planes that isn't a complete swing and a miss, right? So there's that first lower bound for x is that, and then let's see here, I'll use blue. The upper bound for x is where the last slice hits. Right, so we've got this all slices perpendicular to the x-axis. There's a first one, there's a last one. You find the corresponding values of x, and those are your x bounds. So yeah, x1 and x2. Is that good so far? Okay. Just like with double integrals then, you fix a value of that variable. So I'm now going to fix a slice. We're fixing x. We're going to look just at that one x slice. We're going to start slicing this up now. We're going to start thinking about y and z going on, but in particular, just for this one x slice. And just like with double integrals, don't worry about the other slices. We'll get them. We'll get all the stuff that's happening over here. We'll get that for other values of x. But we need to understand not the total ranges of values of y and z. We need to know how y and z range per each x slice. So we fix an x slice. All of our attention now will be focused on this one x slice going forward. Okay. And then, repeat. Right, so next step. Pick your next coordinate axis. Now, no particular reason, arbitrarily, I'm going to pick y for my next coordinate axis. Let me recognize x was our first one there. So now we're going to slice perpendicular to the y-axis. The geometry does get a little thoughtful here. We've got this three-dimensional solid. We've taken an x slice of it. That's giving us kind of a two-dimensional surface, kind of a slice. I now need to slice that perpendicular to the y-axis. You got to think about, how do y planar slices intersect this x planar slice? And I appeal to your geometric intuition that for a given value of y, a y slice is going to intersect our x slice in, the slices are going to be kind of like that. Going to be little vertical segments. Yeah? Okay. Got to think about first and last. Our first slice is going to be there, which corresponds to a lower bound for y. Our last slice, our last y slice of that x slice is going to be here, which corresponds to that value of y. And so our y bounds go from there to there. Now notice where those are, where this lower y bound is, where this upper y bound is. That depends on which x slice you're looking at. Right? If you're taking an x cross section over here, totally different cross section, totally different y bounds. So these bounds all depend on x. They are functions of x, and notice that is so indicated, right? These are functions of x as they should be. Everybody happy? Okay. All right. Then again, we fix a value. Oh gosh, I'm going to have to just redo this whole thing. Don't forget we've already fixed x. We are focused on only this x slice. Now, we're going to fix a y. So we're going to look only then at this y slice of that x slice. If this were a double integral, we'd be done. With a triple integral, so we have to keep going. Now, for that value of x, for that value of y, looking at this y slice of this x slice, I want to know what's the range of values of z. And so, okay, well, z starts at that kind of bottom point there. Z ends at, well, this kind of top point there. Both, depending on both x and y, because, well, yeah, sure. I mean, as x varies, as y varies, this whole little purple situation is going to change dramatically. These bounds are going to depend on both x and y. Okay. All right, so that's kind of what our picture looks like. Notice it is unavoidably picture-oriented. There's a lot of art that goes into, or at least, a lot of drawing skill that goes into being able to make sense out of these bounds and to be able to come up with right answers. We got many examples coming, by the way. I see that we're over time. So anyway, but this is the big picture strategy. And now is the time, if you feel like you're not very good at drawing three-dimensional pictures, now's the time to start working on that. Because we're going to be drawing a lot of three-dimensional pictures doing triple integrals. Y'all have a good day. Good to see you again.